And now potentially one of the most confusing topics in Stats 1 is the normal distribution, mainly because it's the first time that we've seen anything like this. And the one thing I would say each time is to do a diagram. As soon as you do a diagram, it makes it a lot easier. So this question here, this is the last one on the 2016 paper. So the time in minutes taken by men to run a marathon is modeled by a normal distribution with mean 240 minutes and standard deviation 40 minutes. As soon as it gives you that information, start off by doing yourself a diagram where the mean is going to be 240. You might want to write down that standard deviation is 40 as well. So this is, if we call this our M curve, our men's curve, and we've got to work out the proportion of men that take longer than 300 minutes to run a marathon. So we put 300 minutes there. Now the mean, which is the same as the median, is 240. So the fact that 300 is to the right of it, it means that halfway is going to be 50%. So if we get an answer which is 0.6, 0.7, it means that we got it wrong because we know this is going to be less than 0.5. So once we've done our curve on the data we know, we transform that into what we call a Z-curve. A Z-curve is a standard normal. And when we had 300 here, we're going to work out what that comparable value is here. And the way we go from this curve to our Z-curve is we do whatever the value is on our M curve, take away the mean. Actually, M probably wasn't the best letter to use. But take away the mean, which is mu, divided by the standard deviation. So the Z value is going to be 300. Take away the mean, which is 240, divided by the standard deviation, which is 40. So that's going to give us 1.5. So we've now got a Z value of 1.5. And we've got to work out that there. So what we do is we have a look at 1.5 in our tables. In terms of working, that is 5, 1.5. Now if we look at 1.5, we get 0.9332. So 0.9332. The values in our table only give us less than 1.5, so that gives us this bit here. If we want to work out the other bit, the red bit on our diagram, we're going to have to take our value away from 1. So our working should look like 1 take away 5, 1.5, which is 1 take away 0.9332, leaving us with 0.0668. So 0.0668 is that one. Nathaniel is preparing to run a marathon. He aims to finish in the top 20% of male runners. So again, what we're going to do, just to make sure that we're getting it straight in our head, we're going to do ourselves a diagram. So we've got our 240, and if you want to be in the top 20%, that's going to need to be down here, because remember 50% is halfway, so we want to know what that value is. So this area here is 20%, which is going to be 0.2. So once we've done our diagram, our M diagram, we're going to convert that into the Z diagram. We're going to work out what this value is here. So that is 0.2. If we go back to our tables, if we have a look on the next page of our table, we get what's called the percentage points. So now we can see that 20% is 0.8416. If we go back to our diagram, 0.8416 would be this 20% here. So 0.2, that's going to be 0.8416, which means if using symmetry, this one down here will be minus 0.8416. So this value here is minus 0.8416. Then what we've got to do, looking at the context of this question, is we've got to get from our Z value back up to find out what our actual value is. And we know the Z value equals our M value, take away our mean, divided by the standard deviation. We know that the Z value is minus 0.8416, which equals our m value, take away our mean, which is 240, divided by the standard deviation, which was 40. Then we rearrange by times and by 40, adding 240. So if we do that, we do minus 0.8416 times by 40 plus 240, and so that gives us 206.336. So that's it. That is the time that Nathaniel needs to finish it. So 206.336. Now the time taken by women to run a marathon is modeled by a normal distribution with mean mu minutes. Given that W plus mu is 0.82, we've got to work out this here. Now that looks incredibly complicated, but if we start to think about what that means, it's not quite so bad. Because again, we're going to do a diagram. Now we've got our mean here. Now let's say, for argument's sake, the mean for the women is 250, and we've got a standard deviation of whatever. Now it's saying here that the probability of our mean plus 30 is 0.82. So let's say then, that's 280. That's going to be 0.82. So again, let's do another one here. So now we're on our Z curve. So this is our W curve. This is our Z curve. But we're after the probability of mu minus 30. So if this was 0.82, this here was 0.18. So if we keep with the 250 here, so if we keep with the W curve, if this was, let's tidy it up a little bit. If that was 250, let me do this symmetrically. Let's start that again. So for the women's, let's say we've plucked the 250 out of thin air, but 280 and 230. No, sorry, 220. That's better. Now I said to the left of that, that was going to be 0.82, and to the right of it was 0.18. Now using symmetry, therefore this here is going to be 0.18. So what we need to do is we need to work out the probability that W is less than mu minus 30, which is 0.18, given that the probability, because this slash, remember, means given that the probability is less than mean. So the probability that it's less than mean is always going to be 0.5, because we're told that it's less than 250, because it's less than the mean, we know that, so it's going to be 0.5. And the probability that it's less than mu minus 30, we've worked out, is 0.18. So it's 0.18 out of 0.5, which equals 0.36. So that's the 2016 normal distribution question. Let's have a look at the 2015 normal distribution question. Okay, so we've got this here, and let's do a diagram. So if it's a Z curve, because we're told that it's a Z curve, so we're going to start off at 0. So we've got to find the probability that it's greater than 1.1, which is going to be this here. If we look up phi of 1.1 in our table, that's going to give us this here. So what we need to do is, 1, take away that value. So if we look up phi of 1.1, 1.1 gives us 0.8643. So 1 minus 0.8643, which gives us 0.1357. Now probability of B. So again, we're going to do ourselves a diagram. So that's minus 1.9, and we want the probability that it's greater than minus 1.9, which is this here. Now, using symmetry, that's the same as 1.9 is here. So if we just look up phi of 1.9, we get, scroll down, we get this one down here, 0.9713. So 0.9713. And we've got to work out the probability that it's in between minus 1.5 and 1.5. So again, do ourselves a diagram just so that we can see. So 1.5 and minus 1.5. So now, if we look up phi of 1.5, we get 0.9332. So let's go back to our diagram. That is that there. So that is 0.9332. But what we can do is we can work out what this bit is here by taking away 0.5, which is the rest of that there. So 0.9332, 0.9332. If we do 0.9332, take away 0.5, that equals 0.4332, which is just our green shaded bit here. So that's in between 0 and 1.5. Now we know that in between minus 1.5 and 0, that's going to be exactly the same. So this bit here is going to be exactly the same because it's symmetrical. So we just need to then double that. So we get 0.8664 for A. Okay, so now we've got to work out the probability that it's A or C. So again, let's do ourselves a diagram so we can see. So here's 0. If we start with C, minus 1.5 and 1.5, we're looking at this here. Now A is that it's bigger than 1.1, so 1.1 is there, so that's this thing here. So if we have a look at this, using the symmetry, that's exactly the same as 1.5 this way, all the way down. So if we just do phi of 1.5 for that, and that gave us 0.9332. And there you go. So those are those 6 marks. So now let's have a look at the next one. And again, we've got something here which is given that. So we should know what to do with that from the past probability questions. But before we get to that, let's do a diagram. So we've got a normal distribution. So we've got an x-curve here with a mean of 21 and a standard deviation of 5. So we're told, given that it's got a probability of more than 28, so that's that there, we've got to find, and the probability that it's bigger than something, given that it's more than 28, is 0.625, so therefore, our value is going to be here, say, so let's call that W. And this probability out of the total red and green probability equals 0.625. So the first thing I'm going to do is going to work out what the probability of x being greater than 28 is. So we're going to turn that into the z curve. We're going to find out what this corresponding value is here. So the way to work out the z value is 28. Take away the mean, divided by the standard deviation. So 7 divided by 5 is 1.4. So in order to work out this one here, we're going to need to do 5 1.4. That's going to give us to the left. So we'll do 1 minus that. So 1 minus 5, 0.4. 1.4, sorry. 9192. That's 1 minus 0.9192, which equals 0.0808. So because, going back to this question, this is 0.808. So it says, given that the probability is bigger than 28, that's going to be out of 0.808. So the probability of x being greater than w out of 0.808 equals 0.625. So now what we're going to do is work out the probability of x being greater than w. If we times by 0.808, equals 0.505. So the probability of x being greater than something is 0.505. So I just didn't say that's 0.0808. So if we times those two together, we should get 0.0505. So we've got to find out the probability that x is greater than something equals 0.0505. So again, we're going to do a diagram. We've got our x curve here. We've got our z curve here. So I want to know what this value is here. So the probability is 0.0505. So therefore, if this is 0.0505 on this side, the other side of that is going to be 1 minus that, which is 0.9495. And if we look that up in our tables, 0.9495 is, put it underlined there, which is 1.64. So that is 1.64. And what we've got to do, that's on our z curve, we've got to then transfer that back to the x curve. So if the z value is 1.64, that's going to equal our x value, take away our mean, which is 21, divided by the standard deviation, which is 5. So 1.64 times by 5 plus 21, that equals 29.2. So if you've got 29.2, that's the correct answer for this one here. Finally, the normal distribution question for the 2014 paper. Again, what I would do is I'd draw a diagram. So we've got the heights of adult females normally distributed. So that means we do a diagram with height of 160 and standard deviation is 8. So we've got to find the probability that's greater than 170. We want to know what that area is there. Once we've done the height curve there, we're going to transfer that to the z curve. We need to work out what this corresponding value is here. Again, same thing. We do the curve of what we know, we then do our z curve, and we want to find out what the corresponding value is. So the z value is going to be the x value, which is 170, minus 160, divided by the standard deviation, which is 8. So 10 divided by 8, which is 1.25. But if we look up, remember, if we look up phi of 1.25, that's going to give us this here. So we need to do 1 minus that. So 1 minus 5, so 1.25 gives us 0.8944. So that's 1 minus 0.8944, which equals 0.1056. 0.1056. I'm sure I got that right. Any adult female whose height is greater than 170 is defined as tall. An adult female is chosen at random, given that she is tall. So therefore, the fact that it says given that she is tall means the probability, the denominator is going to be out of that. So therefore, for part B here, the denominator is going to be out of 0.1056. So that's the probability that she's 170 or more. Find the probability that she has a height greater than 180. So what we now do is we work out the probability that this person's height is 180 or above. So we've got 160, we've got 180, we would do that one. So we turn it into the Z curve, where the corresponding value now is 180 minus 160 divided by 8, which is 2.5. And remember, phi of 2.5 is going to give us this value here. So we'll do 1 minus that. So 2.5 gives us 9938. So 1 minus 0.9938, which equals 0.0062. So going back to the question, it says given that she is tall, so it's going to be out of 0.1056, so it's going to be 0.0062 out of 0.1056. And that equals 0.5, sorry, 0.0587. Three significant figures. Okay, so for part C, half of tall adult females have a height greater than H. So the probability that an adult female is tall is 0.1056. So half of that, the probability that half of them is going to be 0.0528. And we've got to find what that is. So 0.0528. And we've got to find out what this value is here. So the way we do that is we work out, so if this is 0.0528, this side here is going to be 1 minus that, which is going to be 0.9472. And if we have a look at our tables here, the closest one to 0.9472 is this one here. That's 9474 because 1.61 gives us a value that's further away. So 9472, the closest is 1.62, so that's what we use. So we're going to say that the Z value is 1.62. Yeah, 1.62. And then we've got to work out what the corresponding female height value is. So we know that 1.62 equals this value here, x, minus the mean, which was 160, divided by 8, which is the standard deviation. So times by 8 plus 160, so 1.62 times by 8 plus 160 gives us 172.96 centimeters. So 173 centimeters, the nearest centimeter. But that's how you do the normal distribution.